Consider the case in which we have n players and the first n-1 players are a team. The remaining player, the n-1th, is an adversary, playing in the attempt to minimize the utility of the team. Instead, the first n-1 players obviously play maximizing the utility of the team. Consider again the picture. We have three players. Players 1 and 2 form a team, while player 3 is an adversary. Consider two different situations. In the first, the team can coordinate the execution of their actions. This is equivalent to say that the team plays as a single player. In the second case, instead, the players cannot coordinate the execution of their actions. Consider the first case. Since the team behaves as a single player, the strategy of the teammates can be any probability distribution over the joint actions that are AA, AB, BA, BB. This means that the sum of the probabilities over the joint actions is constrained to be 1. So, for instance, the teammates can play the probability distribution reported in the picture, where probability 0.5 is assigned to AA and BB, while probability 0 is given to the other joint actions. Focus on the situation in which the teammates cannot coordinate. In this situation, player 1 and player 2 cannot reach any possible probability distribution over the joint actions. Specifically, the strategy of player 1 is such that the sum over the probability to play action A and B is 1. The same for player 2. In other words, in the case of coordinated teammates, the teammates reason over the joint space of actions, while in the case of uncoordinated teammates, each teammate reasons over her strategy. So, for instance, they cannot reach some probability distribution they can reach when they are coordinated. In particular, they cannot reach the probability distribution in green, the probability distribution maximizing the probability over AA and BB is that one in red. The impossibility to coordinate introduces inefficiency. Consider, for instance, the case in which the utility of the team is that one in the picture. The best strategy for the team when teammates can coordinate is exactly the probability distribution used before, putting 0.5 over AA and BB. In this case, player 3 randomizes uniformly over A and B, and the utility of the team is 0.5. Instead, when the teammates cannot coordinate, the best strategy is that each teammate plays each action with probability 0.5. However, in this case, the team has a utility of 0.25, that is the half of the utility the team receives in the coordinated case. Focus on the derivation of the mathematical program to find the maxmin strategy for this case. When teammates can coordinate, the problem is a standard two-player maxmin problem. So we focus on the case in which the teammates cannot coordinate. That is the most interesting case. As usual, we have a minimization problem defined on the strategy of the team adversary in red, and we have a maximization problem defined on the strategies of the team, where each player has a different non-join strategy. Focus on the minimization problem. This problem is linear in the strategy of player n, as it happens for the two-player case. So we use strong duality to substitute the minimization problem with the maximization problem, obtaining this maximization problem. However, differently from the case with two players, this mathematical program is not linear, but non-linear. The nonlinearity is due to the product of the strategies of the members of the team. Some results are known. First, the maxmin strategy always exists and the value is unique. The maxmin value may be not rational, and this happens even in games with two team members and two actions per player. Finally, it is known that finding a maxmin strategy cannot be done in polynomial time in the worst case, even when the team members are two.